In the first of our two-part lecture series on work and energy, we're going to talk about work. In the physics sense, work is defined as a force that causes an object to be displaced or moved in the direction of the force. So you exert a force on an object, that object moves in the direction of the net force. Mathematically, we say that work is the dot product of the force vector and the displacement vector. So what that looks like, this thing right here should be a dot. So really it's work is equal to F dot D. Okay, and we know or we recognize that both force and displacement are vectors. Work is a scalar value. It can be positive or negative. We can do positive work on a system. We can do negative work on a system. But it is still ultimately a scalar value. Now, you might have been introduced to this idea of a dot product in math at some point, but it's really just a specific way of multiplying vectors, and it's equal to the product of the two values and the cosine of the angle between them. So if we expand F dot D out, it looks like this. Work is equal to force times displacement times the cosine of the angle between them. And as we said on the previous slide, the dot product always gives a scalar quantity, so work is a scalar value. Now, if we take a look at what this ultimately means, if I have some force that's being exerted at some angle, so that's our blue line here. Okay, imagine that we're dragging a box across some surface. Box. And this is a rope that's tied to that box. So, or you're pulling a wagon, right? And you've got the handle of the wagon and it's up at some angle. The net force is along this blue line. Here's our angle. So looking at our trig, we see that, or we know that cosine of the angle is equal to adjacent over hypotenuse. So the hypotenuse, which is our net force, F net cosine theta equals the adjacent side. That's this reddish piece down here where it says FD. If you're dragging a box along the floor, then that box is moving parallel to the floor. It's being dragged along the floor. So really what we're doing when we find the dot product is we're multiplying the component of the force that is in the same direction as the displacement. Because when we talk about work, work is only done on an object when the force and the displacement are in the same direction. And if they're at some angle, then only the component of the force that is in that direction does work on that object. Now, looking at the units for this, work is force times displacement, so our units then are newtons times meters, and 1 newton times meters is equal to kilograms times meters squared per second squared, because our newtons, as we know, are kilograms times meters per second squared, mass times acceleration, times m over 1, which ultimately leads to this value here. With this idea of work being force times displacement in the direction of the net force, a couple things to keep in mind. If the displacement is 0, then there's no work done by the force. One example of this is standing around holding a box or holding anything in your hand. If you're holding something in your hand, you're exerting some upward force on it to counteract gravity. You're not moving the object. If the object is not moving, then you're not doing any work on it. That doesn't necessarily mean that you're not getting tired, especially if it's particularly heavy, but you're not doing any work on the system or on the object in the physics sense. So no displacement, no work done. Likewise, if the net force is 0, then no work is being done. And so again, the idea of net force. So if the system is in equilibrium, meaning the forces are all balanced, then the net work done on the system is 0. Cart sliding across a frictionless air track at a constant velocity, the net force is 0, so there's no work that's being done on that particular system. And then the other time that we don't have any work done is if the displacement is perpendicular to the direction of the applied force. Perpendicular. So mathematically, the reason for this is that if the angle is 90, then the cosine of that angle is 0. So FD times 0 is 0. Displacement and the force are perpendicular, no work gets done. And really, the reason for this is because there is no net force in the direction of the movement or in the direction of the displacement. And then finally, we have work graphically. And we've looked at a lot of different graphs and a lot of different physical quantities that we can establish from graphs using things like the slope and the area. And in this case, we have work equals F times D, or F dot D, but ultimately we're multiplying the force times the displacement. And so as we've seen in a number of previous relationships, when we multiply those variables together, that's an indication that the area under a graph of those variables is going to give us some physical quantity, which in this case is the work. So the area under a force versus displacement graph is the work done on the object. Now, as we said, we can do positive or negative work, and we'll talk about that a little bit later. But ultimately, it is just the area. And that's pretty much it for work. We'll come back around and talk about it again a little bit more as it relates to energy in our next video.